In today's lecture, we will discuss about the shear stress, shear strain, and modulus of rigidity. Actually, the stress or strain produced because of a force applied tangential to the surface of the body, it is designated by this, is termed as shear stress. And because of this kind of forces or stresses, a deformation of the body will be considered like this. And this angular deformation designated by phi is termed as shear strain. So because of the tangential force, a stress produced is called shear stress, denoted by tau within limit of proportionality. Tau is proportional to phi, that is shear stress is proportional to shear strain. If we replace it by an equality sign, then we must have to introduce a constant designated by capital letter C, or some authors they will designate it by letter capital G also. So C or G, that is modulus of rigidity. Tau is equal to C phi, or C is equal to tau by phi, that is modulus of rigidity is equal to shear stress upon shear strain. Basically, the deformation is not like that. If we go to the actual deformation pattern, whenever we apply a shear stress like this, there must be an equal stress develop on the opposite faces, denoted by tau dash, or that will equal to tau. This tau dash or tau is termed as complementary shear stresses, which are generated automatically. Because of this, the deformation pattern will be like this. The actual deformation pattern of the body will be like this. So this is half phi and this is half phi. Actually, the analysis of this is quite critical, so we are considering, for simplicity of analysis, the deformation pattern like this, and it is from this analysis we'll get approximately the correct value. So shear stress, shear strain, modulus of rigidity, as well as complementary shear stresses. Because of this kind of pattern, you can see that diagonal, say this is A B C D, A B C, and this is D. So diagonal BD gets elongate, and at the same time diagonal AC gets compressed. There will be a compressive force, there will be an tensile force acting along the BD, and compressive force acting along the AC. Right. The another thing, which is your bulk modulus. Bulk modulus related with the volumetric stress and strain. Volumetric stress and volumetric strain, from where we will have another elastic constant, that is bulk modulus. Bulk modulus. So if we are having an hydrostatic stress, or we can say that stresses from all side of the body, which will try to deform the body in a way like this. Say this is x direction, this is y direction, this is, say, z direction. So if we see the stresses from all sides simultaneously acting, then this is termed as volumetric stress. Say this is sigma x, this is sigma y, and along z, say this is sigma z. Volumetric stress, normally denoted by sigma v, is proportional to volumetric strain, that is epsilon v, within limit of proportionality. If we, that is Hooke's law, if we replace this proportionality sign, we have to introduce another elastic constant denoted by K, and this K is termed as bulk modulus. So the bulk modulus is equal to volumetric stress upon volumetric strain. This is another elastic property. If we get the cuboid or cubical element as x, y and z dimensions, initially say in x direction there is x, in y and z, these are the three dimensions, and due to these stresses there are certain changes, say del x along x direction, del y along y direction, and del z is the changes along say z direction. So if we go through these parameters and find out the volumetric strength, so by simplifying we get that epsilon v is basically equal to epsilon x plus y plus z, means longitudinal stress in x direction plus y direction plus z direction will give you the value of volumetric strain. The another elastic constant is your Poisson's ratio. Poisson's ratio, normally denoted by letter mu, that is Poisson's ratio. Lateral strain upon longitudinal strain. This is what basically the Poisson's ratio, lateral strain upon longitudinal strain, and for most of the engineering material the value of this mu lie between 0.25 to 0.33, 0.25 to 0.33 for most of the material. So lateral strain upon longitudinal strain, if we have a bar like this and applying a longitudinal force say P, because of that its length gets elongated and at the same time its diameter will be reduced. So the lateral strain is your del D by D. Across the force is your lateral strain, and longitudinal strain is your del L by L. Of course one will come out with the negative sign. So the value of Poisson's ratio is termed as lateral strain upon longitudinal strain. So the very first thing which we have already discussed in the previous lecture is your E, that is Young's modulus. Young's modulus, or termed as modulus of elasticity. The very first elastic constant, second is your modulus of rigidity, third is your bulk modulus, and next is the Poisson's ratio. So there are certain relationship between all these elastic constant which we will discuss in the next topic.